big thing that we wanted to focus on was avoiding traditional quote-unquote netcode engineering. That building a multiplayer game traditionally is a really, really hard problem. Figuring out like how networks interact with each other at low latency. This is some of the hardest programming in games. And we said, well, how can we design a game that doesn't have to do the real-time netcode engineering? And in doing so, we looked at a couple other game design challenges that we wanted to overcome. The first was, what happens when our game is not popular? This is a like small independent game. We're not going to be actively maintaining it and shipping new content. Eventually, there are going to be 0 users, basically. And so there actually was a Flappy Bird MMO that was built in 2014 or whenever, and it's still live. But if you go there, no one is ever playing with it, and it's functionally not a multiplayer game. And so, oh, there's a video. Cool. And so on the other side, there is this whole genre of these hyper-casual mobile games, sort of .io games, where you're playing against a massive group of players. And the way they solve this problem is you're just entirely playing against bots. It's usually really easy to tell because you can turn on airplane mode on your phone, and the game still works, even though it's allegedly online. We didn't want to do this. For one reason, we were lazy and didn't want to build an AI, but it also sort of felt like we were cheating. Like, if the promise of this game is that it's a battle royale where you're playing against 99 other players, those kind of need to be human players. Which led us to realize how much easier we had it than a lot of these other games. Like in a .io style game, you're usually directly competing with other players. You need to interact with them, you need to shoot them, or whatever the verbs of your game are. But Flappy Bird is more or less, or Flappy Royale rather, is mostly competitive solitaire. You're seeing everyone, and the excitement of the game comes from seeing the giant herd thin out, but these aren't physics objects. You're not bouncing off of other birds. So because you're not actually interacting with other players, what other players do doesn't affect your game other than psychologically. We don't actually need that networking to happen in real time. So we landed on this ghost system where when you go to play a game, we are going to go to our servers and say, hey, this is the level we're playing. Give me recordings of the 99 players who most recently played this level. And so it sends you those recordings, you play your game, you do well, or you probably do poorly, and then we take the recording that we just made of everything you did in game, and we send it up to the server for the next player to use. This is great. Because it isn't real time, we avoid a lot of these really, really hard real-time networking problems. And it even means because we're just storing these recordings and reusing them, we can theoretically offer an offline mode. If we reach a point where there are fewer people playing the game, you don't have to wait around for 99 other players to join. There is always a new exciting game for you to play with players you've never played against. This solves so many problems. So we started out implementing this, sort of building the simplest version we could. As you're playing, we started recording what you were doing. We kept track anytime you tap the screen to flap, we recorded a timestamp, and we recorded when you died, and we would play back, in real time. We would create a bird as if it was a player. Anytime that sort of flap action came in, we would apply a physics impulse as if an actual user had pressed the screen. We also had to add in the sort of y-axis sync because we found, most game engines, unless you do a lot of work, are not deterministic. Which meant in broad strokes that, if I take the recording of me flapping and I play that back synced exactly, it's still not going to be exactly the same. The physics engine is going to act differently in ways that meant you would often fly right through a pipe. So we just said, every 50 milliseconds or every 100 milliseconds, let's store your Y value of your position. When we reach one of those values as we're playing back the recording, we're just going to snap your Y position there. That worked really well. And so then we needed a way to actually get and receive these recordings. And we started using Firebase, the Firestore, which if you're not familiar with it, it is a real-time database where real-time means on the order of 150 milliseconds, maybe, depending on a whole bunch of different factors. They're sort of real-time enough to build Google Docs, not real-time enough for a traditional game. We just sort of picked it at first because it was really easy and quick to get started. It was fast to integrate and relatively low latency. And we started out with really 3 different methods. So we were hitting Firebase directly to read our recordings and to write new recordings to it. And then we also needed a way to deal with level seeds.